Alright, so space. This is our first real space video. We're going to talk about a bit about gravity, a bit about what the border of the atmosphere and in between, so basically between the border of the atmosphere and back to Earth, what it is, why it is. Okay, so here we've got Felix Baumgartner or whatever his name was, who jumped off a hot air balloon, a very, very fancy hot air balloon, and parachuted or skydived back to Earth from, they say, the edge of space. And we'll get to where that is in a minute, but the very, very edge of our atmosphere. So we talked about in the last video how gases move and the average distances apart of them at standard temperature and pressure. Now, I think you can imagine that the further away you get from Earth, the further that distance is. I think the distance was 30 diameters, so 30 diameters of the atom. Now, as we get further away, the distances become much, 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 much further apart. Okay, so let's get into it. What's the point? By the end of this, you should be able to tabulate the various components of the atmosphere, and you're going to do that. You should also tabulate the various areas of the atmosphere. So here are the different areas, and you're going to talk about what's within those. And you're going to explain how gravity affects these different components. And yeah, cool. All right, so as soon as you're finished here, my tip would be to you is if you can get a hold of a copy of the recent Cosmos series starring Neil deGrasse Tyson, the first 5 minutes of episode 12 talks about the atmosphere on Venus, which is very, very similar to ours, but has one major difference, and that's why it's, compare the two. And you should see that. Like, that's actually really, really cool. All right, so the atmosphere composition. Basically, our atmosphere is mostly nitrogen, a little bit of oxygen, then there's some other stuff thrown in there. Okay, so this one here, by the way, argon, which is the third most abundant gas. We can't breathe that. We can breathe it in. It doesn't hurt us because it just doesn't react with anything. It's fairly inert, or it's completely inert. So the atmosphere is primarily nitrogen gas and oxygen gas, and see that it is N2, so it exists as molecules of two nitrogens stuck together, two oxygens stuck together. The gases are held on Earth thanks to gravity. Basically, this means the lighter gases are able to be more prevalent up in the upper atmosphere. So the gases are more concentrated closer to Earth. The Earth is thicker, and this is why the higher you go, the harder it is to breathe. Okay, so here we have the different layers. Now, this is not going to be super clear in the video. You're going to find these yourself, basically. Also, yeah, basically you're going to find these yourself, and you're going to fill in the information. But the layers that we talk about are, we've got the upper atmosphere, so you've got the exosphere and the thermosphere. Now, the exosphere, that's where he jumped from at about, I'm not even sure, you probably look up, you can look up the actual height, just 1 second. Alright, so I looked up where Felix Baumgartner jumped from. I also learned his name, and we'll talk about that in a second. Let's bring my pen back. Yeah, that one. Alright, so you've got the exosphere, that's the furthest out layer. Basically, that's actually where the molecules kind of drift off into space and leave, and they're pushed away by solar winds. So gravity would keep them at Earth, but solar winds come along and push them away. They've got the thermosphere, the temperature goes right up, and that's basically because of the large amount of solar radiation that is absorbed just there. Then we've got the mesosphere, so this is where shooting stars happen. So this is basically where it starts to get a bit thicker. So space debris burns up as it hits their shooting stars. Then we've got the stratosphere. Now, where did Felix Baumgartner jump from? About here. He jumped from 40 kilometers up. So he hadn't even left the atmosphere yet. But that's cool. We're not taking it away from him. It was a very high jump, and he probably is lucky he didn't die. So, and then we've got down the troposphere, and this is where weather happens, and this is what we breathe, and it's cool. All right. So, if you go back to that first page over here, here is height, altitude in meters, and that's temperature. And you see the temperature decreases, increases, decreases, increases, and it's just a cool pattern. Anyway, well, there are good reasons for that, and we should be able to explain those by the end of the unit. Now, this is what I want you to do. You're going to tabulate this. The independent variable is the left column, okay? And you're going to come up with your own table. So this is all Googleable information. You should be able to find this all by Google if you can't read that. All right. So your independent variable, the one that you're changing, is your layer. Now all of the others, height, feature, so something special about it that makes it interesting, description of it, temperature range. They are the dependent variables because they're the things that you're looking up based on whether you're looking at the troposphere and all of the other layers down. So that's your job now. You can pause the video and come back to it, or you can finish it and check it out in a minute. All right, so Newton, the man, he came up with the law of universal gravitation, and what that means is that essentially gravity is attracting everything. Okay, so let's write this bit down here. Gravity is an attractive force, and any two bodies in the universe will attract each other. Now, the force is not equal, okay? It's directly proportional, which means, you know, it changes with their masses. So if the mass increases, the force goes up. Masses go down, the force goes down. That's what proportional means. And inversely proportional to the square of the distance between them. What does that mean? That means that the further you get away, so if the distance between them increases, the force decreases. And because it's the square, you actually get this shape, okay, that shape graph. So it's a very, very rapid drop-off, and we call it exponential. And exponential means that it doubles or halves, either way, it doubles or halves each, you know, unit of distance. So that's cool. All right. The formula is, so force between two objects is gravitational constant. That's just this number here. It's just a number you need. You don't need to know that. It will always be given to you if you ever have to do anything with it. Gravity times mass 1 times mass 2, okay, divided by the square of the distance between them, and that distance is in meters. So tomorrow we'll do a couple of calculations, so I want you to write that down, and it'll just be for practice, basically. All right, so what are the implications for this in the atmosphere? Well, Earth has a very large mass compared to the individual gas molecules. So to be fair, every single one of those gas molecules pulls on Earth, but it's negligible, okay? Because the Earth, the most significant effect is the Earth, because it's so huge, and it pulls them around the Earth. So gravity pulls all the gases to Earth. Further away, the weaker gravity's effect, and that's because of that, where it was basically divided by R squared. So because that divided, so actually we'll go gravitational constant m1, m2. So when we talk about it based on that formula, you can see that the further away you get from Earth, the gravity gets much, much weaker, and it happens really fast. The gravity, you know, decreases very rapidly. So the Earth's atmosphere extends to about 3,000 kilometers, but obviously it's really, really thin at that height. Now, remember, Felix Baumgartner, they say he jumped from the edge of the atmosphere and not even close, but you definitely couldn't breathe there without the equipment. So the concentration of Earth's atmosphere stays fairly constant for the first 100 kilometers. We have a very small range that we can breathe in. So the higher you go, if you go to the top of Mount Everest, it's hard for nearly every single person to breathe without oxygen, so without oxygen tank. So we have a very narrow range, but it's still relatively consistent. As the moon has so much less gravitational pull, it can't contain an atmosphere. It actually does have an atmosphere, It has an atmosphere of about 0.5% of ours. So it holds about 0.5% of the gas that Earth does, and it's all helium. So yeah. And that, by the way, just interesting fact, that helium gas has come directly from the sun. Like it's been blown there, and as it goes past the sun, a very, very, very small amount of it gets trapped around the moon. And that's cool. There's facts for the day. All right, do your table, and we'll see you in class.